As we start to look at chapter 10, this whole chapter is going to be covering circles and different parts that we have for circles. If you notice just from this first section, we have a lot of new vocabulary words. I've encouraged at the top of your packets that you start going ahead and filling out your vocab, so that way you have it. You can either do it from the video. They will be, most of them are inside this video, but it would also be good just to look it up in the book, in the glossary, and just write down the straight definitions, and just kind of get familiar with them. So as we first start to look at circles, we need to know the different kinds of parts. So first, obviously, you need to know what a circle is. A circle is whenever we have all these points that are in a plane that are equidistant from a given point. So that's the outside. All the points on the outside of the circle, they're the same distance from the center. And so whenever we name a circle, we call it by that center point. So like in this example that we have over here, we have circle P, or there's an abbreviation form of where it's like a circle with a dot in the middle of P. Okay, so that's the name of this circle. Then we need to know the different parts. A lot of times we already are familiar with radius. Radius is from the center to the outside. It's that distance. And so that line, we call it the radius, that segment. A chord is any segment whose endpoints are on the circle. So if you notice the chord here, it has a starting place, and then it has an ending point on the circle. A diameter is a chord that contains the center of the circle. It goes straight through the center. You also should know it's twice the radius. A secant is a line that's going to intersect our circle with 2 points. So it's like a chord, but it keeps going. It doesn't just stop. It doesn't just have endpoints on the circle. It keeps going all the way through. And then a tangent is another line that's going to intersect with our circle, but it only intersects at one exact point. Okay, it's just going to barely touch the edge of the circle and keep going. And so that point where they intersect is called our point of tangency. And so that's what you can see in this picture. A point B is the point of tangency to this circle. So first we just need to be able to identify all these types of parts. So here they have several different just scenarios. They have lines, they have rays. And they just tell us to name them, whether or not it's a radius, a chord, a diameter, a secant, or a tangent. So if we look at the first one of AC, notice AC doesn't have any arrows on it on the top, so that means that AC is a segment. So if I'm just thinking about it, it's a segment of AC. Okay, so segment AC goes from the middle, the point C is in the middle, and then it goes to a point on the outside. So if you look back, we have from the middle to the outside, from the center to any point on the circle, it's called our radius. So that means that A is going to be our radius. It is one of our radius. In B, we have AB. Again, it's a segment. There's no arrows on the end of that. Well, AB goes to both the outsides of the circle. So it will look like it's a chord, because a chord has endpoints on the circle. Okay, but in this case it also includes the center of the circle of C. And so if it includes the center as well, and it goes through it from edge to edge on the circle, that means it's our diameter. For C, we have a ray, because it only has one arrow. So ray DE. Well, if you notice, DE just goes along the outside of our circle. It's not touching at 2 points. It's just touching at one point. This point of B would be the only point that it touches. And so if we look back what a ray is, it says here the tangent ray. They are also called tangents. So C is going to be a tangent ray. Okay. And then the last one of AE, notice it has arrows on it, so that means it's a line. AE would go through 2 points of our circle, and it's actually, this is the point E out here. So it goes all the way through our circle. That line AE goes through it. And so when the line goes through 2 points of our circle, that's what's called our secant. So that would be a secant of the circle. Now if we had done like AG and we had done just a segment, that would have been a chord. But since we did AE and it has the arrows on our AE up there, then it's a secant. So now that we've seen the different kinds of parts of our circles, we're going to bring in some of our previous things that we've seen in geometry. So this talks about coplanar circles. Okay, coplanar is a word we had a very long time ago. We haven't talked about it in a while. So coplanar is whenever they are on the same plane. So if we have two circles that are on the same plane, they have different points of intersection, or they could just not intersect at all. So if we have where they intersect at two intersection points, we just say that they intersect at two intersection points, like this first one. If they only have one point of intersection, that's what we call tangent circles. We call those circles to each other tangent circles. And they can be two different ways. Either the circle can be inside, like this first one is, it's inside it. Or we could have on the outside, the second one. Again, they only share at one point of tangency. Okay, this point in the middle, that's our point of tangency. And so we call them tangent circles. And then we have where they don't intersect at all, this last version. But we have certain coplanar circles that don't intersect, but we can call them concentric circles, and it's when they share that center point. And so then if you look at this last part, one more thing we need to look at before we move to the next problem. We have common internal tangents and common external tangents. And this will become easier to understand when we do the example. But internal tangents intersect a line if we draw it between the two centers of the circles, and external tangents do not. So if we look at this first one, it says we're going to do blue to indicate external, we're going to do red to indicate internal. But first what I'm going to do is I'm going to just connect the centers of my circles, because that's going to be able to tell me whether or not I'm doing internal tangents or external tangents. And so when I'm looking for tangents, all I'm doing is I'm trying to connect just one point on each circle. So if I look at kind of on this outside here, it's really hard to draw and I'm not going to get very close. But ideally I'm wanting these to touch just one point on these circles. And that would be one external tangent. I would have another one if I went from this dot to this dot. Okay, that would be another external tangent there, those lines. Then an internal tangent would be ones that connect going through the center. So a tangent would be somewhere in here, there'd be one, and then going the other direction, I would have another internal. And then the second one, I would do the same thing. So I would try to find my externals. I just try to connect my two outside lines of my circles, which again, it's very hard to hand draw this. Well, that one I did a lot better. And then the internal one for this point, it would only be one point. Okay, it looks like we could do one in the middle there. And then our last one, since the circles actually intersect, there's not going to be any internal ones, but we can once again do two outside ones again. Alright, so to make it a little bit easier for you to see versus my beautiful drawing skills, here they are again on the bottom. Okay, this is from the book. It's a lot easier if you have rulers and you're trying to connect it. You can connect it using rulers a lot of times. But as long as you understand internal tangents, they're going to connect one point, one or 2 points of tangencies between the two circles, but they go through the center of the circles whenever you connect their two centers. And then the externals are just on the outsides. So now we're going to get back into some solving. In this first theorem that we have, the tangent line circle, it tells us that a line is tangent to the circle if and only if it's perpendicular to the radius that would go out to that endpoint. And so it just makes that right angle there with the radius. And then we also know that the tangent segments from a common external point are congruent. So if we look at this first one, it asks us, well, is ST actually tangent to circle P? So is ST actually going to touch at one point, or is it going to actually intersect with two? And so the way that we can do this is we're going to use that theorem that we just looked at, the very first one, this top one here where it shows us that we have a right angle. So if this was true, if it is tangent to it, then it would make a right angle here with this radius. Okay, so that would mean it would have to make a right triangle. in order to make a right triangle, just like we did in chapter 9, that means it would have to follow Pythagorean theorem. So our a squared plus b squared, and then hopefully it's equal to c squared if we want it to be right. Okay, a right triangle. So if we plug in our parts, c has to be our hypotenuse, the longest side, and then a and b, it doesn't matter. So if we plug them in, we're going to get 35 squared plus 12 squared. We don't know yet what sign it's going to be. We're hoping it's going to be equals. And then 37 squared. So as I plug these in, I'm going to write out the equation. And so when you square each of them into this next step, 35 squared is 1,225, 12 squared is 144, and then 37 squared is 1,369. Then I need to actually add my first two, keep solving it. And so when I add those two together, I get 1,369. And so if I look at it, my sign now is going to be equals. Okay, those two sides are equal. So that means that this is a right triangle. And therefore, ST is going to be tangent to circle P. So my answer up here is going to be yes. Okay, but you have to have all this work. Don't just think that you can look at it and say, oh yeah, it looks like it's tangent to it. No, if you do not have the work, you will not get the credit for it. You need to be able to know how to solve this. Otherwise, you will not be able to pass the quizzes. So in this next one, they actually tell us, they say point B is the point of tangency. So that means that it is instead, we already know this is a right angle. Okay, they gave that to us. And it wants us to find the radius. So once again, we're going to use Pythagorean theorem. Okay, because we have a right triangle, and that's how we solve to find sides in a right triangle. And so if I plug in my lengths, let's look at where they're going to be. So first, across from the hypotenuse, we have our C, and then we have A and B. So for A, I'm going to put in 80 squared. For B, I'm going to put in R. And then C, we have a whole length there. Okay, so for C, I'm going to have to write that whole thing in parentheses. So the length for C right now is 50 plus R. And then I'm going to square it. Okay, so then you just keep solving this like normal. So 80 squared is going to give me the 6,400 plus R squared. And then the second part, though, you're either going to have to FOIL it, multiply first, because you have to multiply both these. Remember, the square is going to look like, if I were to rewrite it out here, it would be 50 plus R times another 50 plus R. And so you can either FOIL this, or I know some people do the box method. Whichever way works for you is what you do, so it's up to you whichever way you feel more comfortable with. So if I do box method real fast, I'm going to do 50 times 50. So basically 50 squared would give me 2,500. 50 times R gives me 50R. Again, 50 times R gives me 50R. And then R times R gives me R squared. And so these are going to be all the parts I can write out together. So I would have 2,500 plus 50R and 50R together. I can combine those because they both have an R on them. So that's 100R plus R squared. And so if I keep solving, notice I have two R squared. So I'm going to try to combine them. So I'm going to subtract R squared from this side and subtract R squared. Here it goes away. So I get 6,400. And then this side I still have 2,500 plus 100R. And then R squared minus R squared, it canceled out again. So actually they canceled on both sides. And now I can continue to solve. So I would subtract my 2,500 from both sides. And then I'm going to write this over here, because I'm going to get 4,000 on the left. And then I still have 100R on the right. So to get R by itself, I divide by 100 on both sides. And so 4,000 divided by 100 is going to give me 40. So that means 40 is going to be equal to my R. So if I write it back up here, R is equal to 40. Okay, it looks like a lot of work, but it's just using Pythagorean theorem. Make sure that you just plug in your size exactly as it is and just work it step by step. Don't get overwhelmed by what do I do with this. Just work it step by step like you know how to do. Then our last example, we're going to use the other theorem that we had. The other theorem told us that if we have an external point that connects 2 points of tangency on our circle, that both those segments are going to be equal to each other. Okay, so if we know that RS is tangent to circle C at S and RT is tangent to circle C at T, it wants us to find the value of X. Well, like I said, that theorem tells us that both these are going to be the same length. So if they're the same length, then I can set them to be equal. And then I just have to solve. So I'm going to subtract 4 and then divide by 3. And so I'm going to get that X is equal to 8. And it just asks for the value of X, so that's my answer.